All right, let's talk about something that sounds like it's straight out of a sci-fi movie, but it's real and it's happening right now. I'm talking about quantum communication. We're going to break down how the super weird rules of quantum physics are being used to build a truly unhackable way to send information. Seriously, let's get into it.
So here's the plan. First, we'll cover the huge leap from the bits and bytes we use today to these new things called qubits. Then we'll get into the 3 wild quantum rules that make this whole thing work. After that, we'll see how those rules create a literally unbreakable code, check out where this tech is already popping up in the real world, and wrap up by looking at the big challenges that are still on the horizon.
Okay, so first up, the quantum leap. What's the big deal here? I mean, how is this different from the regular old internet we're using right now? Well, it's a total game changer. Okay, so think about it like this. On one side, you've got our current classical communication. The internet, right? It's all just electrical signals. And the problem is, those signals can be copied or intercepted, and you might never even know what happened. But on the other side, that's the quantum leap. We're not using signals anymore. We're using the quantum states of individual particles, like photons. And here's the absolute key. The security isn't some clever bit of code. It's built into the laws of physics themselves. You literally can't break it without breaking physics.
Which of course leads to the big question: how? How can physics itself make something secure? Well, that brings us to the really fun part, the 3 quantum rules. You really got to wrap your head around these 3 weird, kind of mind-bending concepts to see why this is so revolutionary. They're basically the secret sauce behind the whole thing.
Okay, rule number 1 is superposition. Now, you know how a regular computer bit is super simple, right? It's either a 0 or it's a 1. That's it. But a quantum bit, or qubit as they're called, is totally different. Thanks to superposition, a qubit can be a 0, a 1, or both at the exact same time. It's like it's in a state of pure potential, which means it can hold a whole lot more information.
Here's the best way to think about it. Imagine you flip a coin. While that coin is spinning in the air, what is it? Is it heads? Is it tails? Nope. It's kind of both, right? It's in a fuzzy state of potential. That spinning, undecided state is superposition, and that's exactly what a qubit is doing before you look at it.
All right, next up is rule number 2, and honestly, this one is my favorite. It's called entanglement. And this is where things get really, really weird. You can actually link 2 particles together in such a way that they share the exact same fate, instantly. So if you measure one, you instantly know the state of its partner, even if that partner is light years away on the other side of the galaxy. It's so strange that Einstein himself called it spooky action at a distance.
Let's use another coin analogy. Imagine you have a pair of, magic coins. They're linked. You keep one, and you mail the other one to your friend across the country. The second you look at your coin and see it landed on heads, you know with 100% certainty that your friend's coin instantly landed on tails. That perfect, instantaneous, spooky connection, that's entanglement.
And that brings us to our 3rd and final rule, and this is the one that ties it all together for security: measurement. See, in the quantum world, there's no such thing as being a passive bystander. The very act of observing, of just looking at a particle that's in superposition, forces it to make a choice. It collapses out of that fuzzy both state and becomes a definite one or the other.
So let's go back to that spinning coin for the last time. As long as it's spinning, it's in superposition. But the moment you catch it, the moment you measure it by looking, the spin is over. It's forced to become either heads or tails. That act of observation fundamentally changes things. And that simple fact, that looking at something changes it, is the absolute key to why this whole thing is unhackable.
Okay, so let's recap. We have our 3 rules: superposition, entanglement, and measurement, the weird physics behind it all. So now, let's put them all together and see how they create a code that is, for all intents and purposes, unbreakable.
So the killer app for all this, the first big thing it's used for, is something called quantum key distribution, or QKD for short. And what's really clever is that you don't actually send your secret message using this method. No. The whole point of QKD is just to create and share a secret digital key between 2 people. Once they both have that perfectly secure key, they can use it to encrypt their messages with regular methods, knowing that nobody could have possibly intercepted the key itself.
So how exactly does this stop a spy? It is so clever. Let's say Alice wants to send a secret key to Bob. She sends it 1 photon at a time, with each photon in a state of superposition. Now imagine an eavesdropper, we'll call her Eve, tries to intercept one of those photons to read it. Well, remember our rule about measurement? The moment Eve measures that photon, she forces it to collapse. She changes its state. So later when Alice and Bob compare a small sample of the key they sent and received, they'll see that something is off. They'll find errors, and they'll know instantly that someone was listening in. Eve literally cannot touch the message without leaving behind a big, obvious footprint.
And you might be thinking, okay, this is cool, but it sounds like science fiction for the year 2200. But it's not. This technology is already moving out of the lab. So for our next section, let's take a look at where quantum communication is actually making an impact in the real world right now.
The potential applications are, well, they're huge. Think about the world of banking and finance, protecting every single transaction from hackers, especially with the threat of future quantum computers that could break current encryption. Or what about governments and defense, securing top-secret diplomatic and military channels? It's happening. Scientists are using it to collaborate securely. And maybe the most amazing thing, we're already beaming these quantum signals to and from satellites, laying the groundwork for a truly global, unhackable quantum internet.
And this really isn't just a small step forward. This quote sums it up perfectly. It says that quantum communication represents a paradigm shift. And that's exactly what it is. It's not just a better lock, it's a completely new kind of security, a totally new way of thinking about how we keep information safe.
But of course, it's not all smooth sailing. Building the future is always hard. And as amazing as all this sounds, we have to be realistic. There are still some pretty big hurdles to get over before we all have a quantum modem sitting next to our router.
So what are the big roadblocks? Well, the number one enemy of quantum communication is something called decoherence. See, these quantum states are incredibly fragile. The best analogy is to think of a soap bubble. It's beautiful, but the slightest breeze, the slightest bit of heat or vibration from the environment, and pop, it's gone. That's decoherence. And that fragility is what really limits how far we can send a quantum signal right now before the information just degrades.
But scientists have a plan for that, and it's brilliant. The solution they're developing is called a quantum repeater. You can think of these as little pit stops along the quantum highway. They're designed to catch a fragile quantum signal, kind of clean it up and boost it, and then extend that precious entanglement further down the line. These repeaters are the missing piece of the puzzle for building a truly globe-spanning quantum network.
And that really leaves us with a massive question to think about. Our entire digital world, everything from your smartphone to the global economy, was built on a simple on or off switch, the 1 and the 0. It's amazing what we did with that. But now, we have access to something so much more fundamental, so much more powerful and secure. So it really makes you wonder, what kind of future will we build when our world is connected not just by bits and bytes, but by the strange and wonderful laws of quantum physics itself?